Hi, my name is Sebastian. Some of you might know me as Sebi06 from ImageSC. I'm currently working for Zeiss Microscopy in Munich as a product owner in the Product Center for Software, and I'm responsible for our AI solutions, our CZI5 format, and some other things. Today, I will share with you some ideas and learnings when we started to create an open ecosystem for data-centric model development at Zeiss. Our mission statement for AI solutions could be described as put the scientist back into the driver's seat for deep learning. Since many of our users are not trained data scientists, it's a lot easier for them to provide more and better data and labels compared to understand how to tweak a model and its parameters in order to achieve better results. One of our core messages when it comes to image analysis and AI solution is better data beat better models. The key idea is therefore to make it as easy as possible for the user to iterate a model with more data and labels. Our current focus when it comes to AI solutions is on the following three areas. Classification is used for sample carrier recognition, object and image classification. Segmentation, all our image analysis tools are AI ready, which means trained segmentation models can be plugged in easily for the segmentation step. Processing is used for resolution improvement, reconstructing and denoising images, including general image-to-image translations. Creating all those tools in a bigger company can be a bit complicated. To give you an idea what this means, I try to list all involved organizational units that do some type of AI development. And since developing AI tools is fun, everybody wants to do something new and move forward quickly, which is good and bad at the same time because everybody is tempted to create its own solutions over and over again. Other challenges in a company are academia wants open and flexible solutions and does not like to be locked in. Industry often wants streamlined and integrated tools and one-button solutions for a specific task. Various open source software tools already exist, so what is the actual business model for us? Cloud computing is trending, but many users do not want and/or are not allowed to use cloud computing yet. What tools and libraries should be used then? Should we develop our own stuff? You can check the icons on the right-hand side to see what our current choices are. Our concept is centered around the trained model, which is the central component of our ecosystem. Therefore, this must be a highly standardized component and it should be easy for everybody to use it. In order to have an open system that allows everybody to use their own models, such a format must be public. To put it in simple words, the concept must allow to train a model anywhere independent from where it will be finally used. One can train in ZEN, on APEER, in a Jupyter notebook, or get the labeling and training from us as a paid service. The implementation of that concept in a bigger organization is not so easy, because alignment in an environment where everybody has a strong motivation and incentive to develop new things fast is very crucial. It is very easy to end up with tons of new tools and a degree of complexity which is hard or impossible to manage. So the main questions for us at Zeiss are, how do we implement such an open ecosystem without driving everybody in software R&D crazy? What components and tools do we need for that? What's the best way to align everybody and create maintainable code and real business value? One of the most important learnings for us here were that one nice way to align different parties in software development is to provide useful tools and APIs that make the life easy, because people will use them without the need to tell them to do so all the time. This is especially true inside a company, and therefore we decided to create our Zeiss machine learning stack. The main components of our machine learning stack are shown here. It's mainly based on Python and organized into open source and internal packages. Everybody at Zeiss can easily use those simply by doing pip install xyz. We have a clear rule that those tools have to be the first choice when starting new development projects. If one needs to extend a package, then please do so. To be clear, this approach also comes with certain responsibilities. Test coverage and code quality standards cannot just be a nice thing to have, but they are crucial to make this concept fly. Now I will give a very brief overview about some of those packages. The first one I want to highlight is the czmodel package. It's an open and standardized container to store machine learning models and its metadata. The czann format is the glue between software tools for machine learning at Zeiss and can be used everywhere. It does not contain a new model format itself. We use ONNX wherever possible. Currently, it's used in ZEN Blue, ZEN Core, on APEER, in Arrivis Vision 4D, and some other internal tools. And since we want an open ecosystem, we decided to make this public to allow external data scientists to use it as well. To learn more about it, I recommend running the linked Colab notebook. The next tool, which I think is of general interest for the bioimage community, is the pylibirw read-write package. The package is based on the new libczi read-write C++ library, which will be published soon on GitHub. One of the main motivations for us to create this package is to let the other developers focus on real application code and not on data I/O topics. The API allows reading and writing parts of the CZI image, which makes it quite useful for AI applications where you hardly process images without tiling. By using pylibirw read-write internally in AI projects, we ensure that the output images work seamlessly in the downstream workflows of our platform. To learn how to use it, please check again the linked Colab notebook. And the last open source package, which I want to talk about here, is the cztile package. When developing AI applications, there's always the need for a tiling method. In the worst case, reinventing tiling for every project is not only a waste of time, but will also create different results. Our idea is to use a general library to create tiles with overlap whenever possible. The cztile package is not limited to CCI images or any specific format because it works on arrays. It can be directly used together with pylibirw read-write to read and write tiles for processing. To learn about its usage, please use again the Colab notebook. So what does the user see? How does this ecosystem look in action? And everything I will show on the next slide is using the mentioned components and the Python packages I presented on the previous slides. So how do we create a data-driven training tool for deep learning models powered by our machine learning stack? The basic idea is to allow the user to focus on labeling parts of the image where the model can really learn valuable information. At the same time, take away the need to label the complete image to encourage the user to do more annotations on more images and do more iterations of the model training. This quick ML feedback cycle of inspection, adding more data and new labels is the key to provide performant models. Or to put it in simple words, better data beat better models. So the first step is upload an image, and the key concept then is called partial labeling, which basically means that the user does not have to label the complete image. One starts with using a simple image and the definition of the desired classes for the training. This can be done easily in the browser on the APEER platform. The next step is to do the actual labeling of objects. The user must label only a few objects precisely in the first step. Be aware there is no need to label all objects in that frame. To allow the model to learn, it is crucial to not only label objects, but also the background class. The user must label the background around labeled objects by just brushing over those. There is no need to precisely label the pixels along the edges between the object and the background, the place where the network needs to learn the most information. To ensure precise labeling of those critical regions, the annotation tool automatically cuts out the background based on the labeled objects. This way, pixel-precise labeling of edges can be achieved very easily. Based on our observations, such ease-of-use features are exactly what convinces many users to label more objects on more images. Using more labeled data for the training is important to create robust models. Often this approach is better compared to tuning models with little data. Obviously, we all know that also better models will help, but for non-expert users and non-coders, this approach is quite powerful. And once the labeling is done, the user just has to press the train button. Reading the image will be now done using pylibirw read-write. Tiling with the required overlap will be done using cztile. The unit is trained in a fully automated fashion on APEER, no coding required. The model and its metadata are exported as a czann file using the czmodel package. And in ZEN, the model can be used inside an image analysis, for example, inside a 3D image analysis pipeline. Or here is an example for label-free segmentation using a deep learning model trained on APEER. The model was imported into a so-called BioApp as part of the segmentation step. The tiling and applying the model to a multi-well and multi-dimensional image is done automatically for you. The image analysis results are displayed nicely, and the cool thing is this would work exactly the same way if the model was trained inside your favorite Jupyter notebook and packaged into a CZANN file. And here is the training UI for our Noise2Void shown applied to an FibZen image. The user can easily train a Noise2Void model here or import his own regression model as a ZEN file created using the czmodel package. This allows not only to denoise images, but also using our software platform to apply specific image-to-image translations using custom regression models. Conclude, here's a short summary with the key messages. Our ML ecosystem at Zeiss is mainly built on a Python stack. Many teams use and contribute to this stack. A very nice way to address the alignment issue is to incentivize the development teams to create reusable Python packages that make the life of the other teams easier. Our idea is to keep the system as open as possible and to make packages public. This also forces us to adhere to certain code quality standards, which is crucial for such a stack. Staying open also allows us to benefit from new development, and it gives the community the option to use their own models on our platform. Thank you for your attention.